Number 6 and 7. Uh-huh.
Okay, so it's f of x is the square root
Mm-hmm.
of 1 minus 5x.
1 minus 5x.
Yes.
So this is homework number 3, right? Homework number 3.
Mm-hmm.
And this is number 6. And what's the question asked? What's the domain?
Yeah,
Okay.
it was simple, but I don't know if I submitted the answer wrong or what was the issue.
So I want to find the domain of this function, correct? Are you able to now recognize what's the parent function? I know that's not part of the question, but you should be able to do this now. What is the parent function? Do you know?
No.
The parent function is the square root function. This is a square root function. So y equals square root of x. This is a square root function.
Mm-hmm.
So that's the first thing we should be able to recognize and identify what kind of function it is on the general. That's why we call it parent function, because from this parent function, there are many other functions that can originate from it. And this is like the major general, the most basic general one. And then we get all of the variations of it, right? We can have several things that occur underneath the radical. Now, one thing we had to remember, that the reason why I bring this up is one thing we had to remember about square root function, just the parent square root function, is that whatever is underneath the radical must be greater than or equal to 0. So the domain represents all the x values that have a corresponding y value, meaning that when I plug in an x value, I get a y value. What's not in my domain are all the x values that don't have a corresponding y value, which means the problem is the square root can never have a negative number expressed because you won't have a corresponding y value for it. You won't have a corresponding output value for it. So in order to find what the domain is, you must make the expression underneath the radical greater than or equal to 0 and solve for x. That's really what this all amounts to. So to find the domain for a square root function, set expression under the radical greater than or equal to 0 and solve for x. Why is that? Because the expression underneath the radical cannot be negative, because then you'll be speaking about or you'll be dealing with uh, complex imaginary numbers, but we're only dealing with real numbers. So there is no real number associated with the negative number underneath the radical. Like there is no such thing. For example, um, I'll give you an example. The square root of -4, right? There is no real number. No real number. It's undefined in the real number world. In the imaginary complex world, there is a numbers. It's a 2i, but we're not going to deal with that. So because that's the case, then we're going to say 1 minus 5x is greater than or equal to 0. That's what we're going to do because our expression underneath, right? This is the expression underneath that we want to make sure is positive or equal to 0, non-negative. That's what we're doing. And then solving this should not be too hard, right? You should subtract by -1. Negative 5x is greater than or equal to -1. We divide by -5. And then what happens? We get x is less than or equal to 1/5. So what did we just figure out? We figured out that all the x values must be less than or equal to 1/5. So then we say my domain, So I can write it in two ways. I can write it in saying that my domain are all the x values that are real, such that
Good question. When
x is less than or equal to 1. Or the interval would be what? Negative infinity to 1/5, and we include 1/5. So we have a square bracket.
oh, it's less than
Okay,
or equal to. It's not. It wouldn't be. Why is it not greater than or equal to again?
because we do a little step here. We divide inequality by a negative number. Remember that? Remember that rule when you divide by a negative number, or when you multiply by a negative number for inequality, the symbol or the sign here, it switches.
Okay.
We switch. Switch sign because we divide by a negative number.
Okay.
So when we divide inequality by a negative number, remember to switch the inequality symbol. And that's why. So maybe that may be the reason why you didn't get it. Make sense? Does this make sense now?
Yeah, I get it now.
So that's all that one is about. You say you had another question as well, number 7, or
No, it's the same concept applies, so it's the same thing.
same idea? Okay, yeah, that's right. A lot of those are kind of similar. So something like this, you should be able to do on the quiz. Like if I give you a function like this, you should be able to know, okay, this is square root, make the square root equal to 0, solve for x, and then be able to write it in interval notation. Okay?
Yes, thank you.
No problem. Everything else is good? Any other questions, guys? Okay, good. All right. So no other questions. Let us continue. We were talking about transformations of functions, right? And we discussed how a function would look if we were to shift it up, vertically shift it up, right? We vertically shift it down.
Oh wait, Professor,
Yes.
I have a question from the homework.
Okay.
Number 22.
Number 22.
Yeah, it was 1 equals radical x is equal to radical x squared plus 1, and then the other one was 1 plus radical x is greater than radical x squared plus 1.
Okay. Yeah, that's actually something I wanted to discuss today, but we can start with this actually. Say that one more time. 1 equals, right?
Yeah, what? No, 1 plus radical x
Okay.
equals radical x squared plus 1. And then
Okay.
the second part of it was just that it was greater than.
1 plus radical x is greater than square root of x squared plus 1.
Yeah.
And what was the exact question?
Solve the given equation or inequality graphically. Say your answer, round it to 2 decimals, and it just says x equal. It wants you to find x.
Graphically, right? So solve the equation, right? Let me. Yeah, so this is something I wanted to discuss today. So we can start with this. Let me just open it up. So for this problem, you need to use your calculator. So this is a more of a calculator question.
So you would have to just like plug the equation into a calculator and then see how it looks on a graph.
Yeah, so okay, so the question is solve the given inequality or equation, right? Graphically. So there's two of them. There's one, this is part A, okay? And the other one is part B. So I'm gonna take care of this somewhere else. So this is part B. Okay, so the moment we see equal sign, right, for part A, we see an equal sign, then we have to, this is an equation. So I am solving an equation graphically. Okay, so then immediately, this is a graphing calculator question, immediately. Yeah. Why is it a graphing calculator question? Well, we don't have at this moment an algebraic way to solve this. You start to see this gets kind of complicated pretty quickly, right? If there was no radical here, then we would have, pardon me, we would have a quadratic equation, and we know how to deal with quadratic equations. We start to see that as we get more and more, acquainted with mathematical equations, we start to see that the equations that we know how to do are very structurally, um, they are kind of things that we know how to deal with, right? For example, quadratic equations, we know how to deal with
Oye,
them. We know
Mike,
how
¿qué pasó con el graphing calculator que tenía?
pardon me?
Es el graphing, el grande, ¿te acuerdas del que teníamos de lavandería? El graphing, el más grande.
Excuse me,
No,
can you
el
mute
grande
yourself? Who's this?
the one that we took from the laundry mat.
Excuse me.
No, it has to work because I used it in high school.
Okay, Daniel, can you mute yourself, please?
Yeah.
Sorry about that. So the problem is that a lot of these questions, right? A lot of these equations, they get really complicated the moment you plug in these radical equations and these radical symbols. Like it gets complicated quite quickly. So there's no real nice algebraic formula for it. There's no square root formula to solve for this, right? So then because of that, we have to use numerical methods. And for now, we're using our graphing calculator because the graphing calculator is designed to do problems like these. So then how do we approach this? Well, we need a calculator for this. So what we're going to do is we're going to set one side of the equation as y1, and we're going to set the other side of the equation as y2. So this here, I can call it y1, and this here, I can call it y2. What we're going to do is set each side side of equation equal to y1 and y2. But this y1 and y2 is not the same as the slope question. So what I'm going to do is I'm going to share my screen, and I'll show you a graphing calculator. So here we have a graphing calculator. Of course, this is an emulated version of it. Hopefully you guys have the actual thing with you. So what we're going to do is we're going to go to y equals. And of course, we have y1, y2, y3. So these are the y1s I'm talking about. So y1, I'm going to say, left side of the equation is 1 plus the square root of x. So that's going to be my first equation. Press enter. And then my second equation here, y2, will be the square root. So second, the square root of 1 plus x squared. Or x squared plus 1, same thing, right? So here we have both of the equations. Now what we're going to do is we're going to graph. So the first blue equation here is the y1, and the red graph here is the y2. Now, I want to figure out when they're equal to one another. So maybe let me zoom in just a bit. So I'm going to zoom in with 2, and I'm going to move it the center of this a bit closer to where they intersect. So when I press enter, I have a closer look as to what's going on. So look what I have. I have the y1, this is the blue curve, and I have y2, which is the red curve. Now, where do they intersect? Where do they cross? So then the question is, the intersection points of these two graphs represent the solution to the equation. That's what it represents. So it looks like it intersects right here. So how do we figure out, does anybody know how we figure out what are the coordinates where that intersect, where the two graphs intersect? Does anybody know how to do this on the calculator? Second trace. Thank you, Cindy. Yeah. So we go to second trace, and then we choose, we say intersect 5. And then we can get close. We can move the cursor with the left and right arrow keys. And then we get close to where they intersect, and then press enter for first curve, second curve. They say enter, and then it's gonna guess, quote unquote, right? It's gonna numerically, whatever it does underneath the hood, we don't really know at the moment, but it does the work. And look what it tells me. It tells me the intersection. The intersection is 2 point. So we have an intersection point of the x value is 2.31, and we only want to, I think we only want to do that 2 decimal places. So 2.31 is fine. And then it says comma 2.52. That's one of the intersection points. And then the other one seems to be where? It seems to be the other intersection point is going to be where they both cross the y-axis, and it should kind of be apparent as to what the coordinates here will be. And if we just try it again, it's going to guess. Whoops, let me do that again. So press enter, guess. Okay, so it's not completely doing it. And the reason why it might be is because it may not intersect. But if you look at it, if you look at the equation, if you go back to the equation, and we see, right, we see in the graph that it crosses both of them cross the y-axis. If you cross the y-axis, so let me just write that down. So y1, right? Y1 is let's write it up here. So I got y1 is equal to 1 plus rad x, and I got y2 is equal to square root of x squared plus 1. So where do they cross the y-axis is when x equals 0. So check, what's the y-axis? Check at y-axis. That's when x equals 0, correct? So if I look at x equals 0 for y1, then I'll get 1 plus the square root of 0, which equals 1. So what's the coordinates? 0, 1. And then x equals 0 for y equals 2. And I get square root of 0 squared plus 1, which equals the square root of 1, which is 1, right? This equals 1, which means that the coordinates is still 0, 1. What does that mean? That means that both graphs intersect at 0, 1. So I have two intersection points. I got 0, 1, and I got 2.31, 2.52. And then they're asking me in the question, they're asking me, state your answers, solve the equation. So when I solve an equation like this, right, what am I looking for when I say solve? I'm looking for what are the x values. So then what are the x values here? So what are the solutions to the equation? Solution to equation. So my x values are going to be bracket 0, 2.31. These are the x values where the intersection points occur for the graph. So that's what it is, 0.231. So does that make sense? Again, this is a more of a calculator question. So if you know how to deal with the calculator, then this should be fine. Okay, so we were able to solve the equation, and then if you notice, you can apply the same technique procedure to any equation now. It doesn't matter what equation it is. As long as you have a graphing calculator, you can graph them and then see where they intersect and use the intersect function for this to find the intersection points. All right, and so then now the next part of this question is an inequality. So it's saying 1 plus square root of x is greater than the square root of x squared plus 1. So again, we have this, we treat this as y1 and we treat this as y2. Now, one way we can interpret this is saying for what x values is y1 bigger than y2? So for what x values is the graph of y1 above the graph of y2? Does everybody see how I interpreted this symbolic inequality as saying that when is the graph of y1 above, bigger than the graph of y2? So then we can go back. We can go back. And then we go back to our calculator and go to graph. So remember, y1 is the blue curve and y2 is the red curve. What we're saying is when, for what interval, for what x values is the y1 curve, the blue curve, when is that bigger than the y2 curve, the red curve? So when is it bigger? We see that blue is above the red in between this interval here, in between the 2 points of intersection. That's why they make you find points of intersection first. So then the x values, everything in between makes this inequality true. Everything outside of this interval, so if it's bigger, if the x values are bigger, then this the x value 2.31 here, right? If their x values are bigger, then the inequality does not hold. The red curve is bigger than the blue curve. And to the left of 0, well, there's no blue curve to even speak of. So then the inequality doesn't really hold anyways. So then what would be the solution to this? So you would say by the graph, right? By the graph, the solution to the inequality would be it would be the x values go from 0 to 2.31. And the reason why we're not including, why are we not including the 0 or the 2.31 with the square brackets is because this is a strict inequality. It is not an equal sign. So if I plug in 0 for x or 2.31 for x, then these two expressions would be equal, but I just want this to be greater than, so it has to be everything in between 0 and 2.31. Okay, so that was what I wanted to discuss. We kind of touched upon it earlier than I expected, but good. Any questions about using the graphing calculator to solve equations graphically? No questions with this? Everyone's clear? Okay. All right, so we'll go with this. Okay, so let's continue with transformations of functions. So far, the only thing we've discussed here was, yeah, horizontal and vertical shifts. So we're going to continue with transformations of functions. So we're going to start with the parent function, okay? And the parent function for now, I'm not going to I'm not going to write a specific one. I'm just going to write a general one. So we're going to have a parent function, y equals f of x. And what we're going to do with this function is several things, right? Uh, we can either say, hey, let's create a new function, y equals f of x plus k. And then what kind of effect is this? So what's the graphical effect? So this is the transformation, right? This is the actual transformation that's being applied. And then this is like the algebraic representation of a transformation. So algebraic representation of a transformation. On the parent function. So what happens when I add a k, or in this case, the k is a constant. So it's like a number. It's like saying +5, +4. So this is a constant. K is a constant. So the graphical effect we know from last time. So making a table might help a lot. Is that we vertically shift. We vertically shift a graph of y equals f of x, k units up. Now, what happens when I do the opposite? Y equals f of x minus k. So if I have a minus number, then I vertically shift graph of y equals f of x, k units down. So I don't need these exclamation points every time, but. So is everybody with me with this?
Yes.
So what we can think about these on the left side, right? On the left side of this table, we can think of these as commands. We're learning how to give commands and how to interpret commands. So these are algebraic. It's kind of wordy, right? An algebraic representation of a transformation on a parent function. You can just think of it as this whole thing as an algebraic command. It's a command. So this is AKA algebraic command. And then on the right side is the effect. What's after I add this k, what's the actual effect of it? What's the transformation actually? Well, it's a shift upward. If I subtract by k, it's a shift downward. And that's kind of apparent, right? That's apparent. But then when we talk about shifting things horizontally, it's not as apparent. And actually, it's kind of a bit counterintuitive to what we would expect something to happen. So now the question is, what happens if I do this instead? If I add the k inside, now it changes the whole effect. It's no longer a vertical shift. It's actually a horizontal shift, but it's not the horizontal shift that you may think. So you see the plus, you're thinking, oh, to the right, but actually it's to the left. So this is a horizontal shift. We horizontally shift the graph of y equals f of x. We move it k units to the left. So when we add a 3, when we x plus 5, x plus 10, we're shifting it to the left by that number of units. So it's opposite to what we normally may think. And then we have the other version of this horizontal shift. So when we have y equals f of x, and instead of plus, it's a minus k, then we have a horizontal shift of sorry, this should be of graph y equals f of x, k units to the right. So you can also think of these as one single group. So these are the vertical shift commands. The 3 and 4 are the horizontal shift commands. So you had a plus k, and the key here is that the plus and the minus occurs to the x value inside the parentheses, and the plus and minus are affecting the function on the outside. So when you add or subtract by a number on the outside of the parent function, you're shifting it up and down. When you're adding or subtracting a number within the parentheses to the x value only, then you're shifting it left and right. So again, these are commands up and down. So now we're learning how to move things up and down, and we're learning how to move things or graphs left and right. So that's the business that we're in at the moment. So those are the first 4 commands, and we talked about them, but now we're talking about them in a more general sense. And now I'm going to give you the rest that you should know. So not only can we shift graphs up and down, left and right, we can also stretch them vertically, and we can also shrink them or compress them vertically. So we can make them elongate on a vertical level, or we can squish them on a vertical sense. So then how do we do that? Well, we can do it by the following way. If we multiply a number, I'm using the number k. A k represents just a number. So if I multiply by a factor of k to my function, does anybody know what kind of effect this will produce? So if I have a parent function and I multiply it by 3, what would be the result? Does anybody know? Okay, I guess not. So if k is bigger than 1, so there's two possibilities. If k is bigger than 1, then there's going to be, yeah, so let me separate. Yeah, let me just leave it like this. So if k is bigger than 1, then there will be a vertical, the result is a vertical shift, a vertical stretch, pardon me, a vertical stretch by a factor of k. So there's going to be a stretch. So if this number is a 3, a million, a 50, 100, if you multiply a function, a parent function by 100, you're going to scale it by 100. You're going to stretch it by a factor of 100. However, if this number is between 0 and 1, then it's going to be a vertical shrink or compression. By a factor of k. So we can shift things. We can compress vertically. So we have to be mindful as to what number is going to be in front of our function. So if it's a number bigger than 1, we stretch it by that number. If it's a number between 0 and 1, so if it's a fraction of some sort, then we're going to have a compression of, vertically speaking, of our function. And we'll do some examples to see it in action. But for now, I'm just giving you all the commands, and then we'll use them later. So the sixth one. So again, this is a vertical. This is a vertical shift or compression command. Now for number 6, we have the vertical. We have the horizontal stretch or compression command. So this is when we have our function, and a number inside of it is multiplying x. So you see how there's kind of a comparison between these commands here and these commands here. So when we add or subtract a number on the outside, it's vertical shift. When we multiply a function on the outside, it's a vertical stretch or compression. When we add or subtract a number inside of the function to just the x value, then it's a horizontal shift. And if we multiply inside the function just to the x, then it's a horizontal stretch or compression. So there's a kind of a connection there with vertical and horizontal commands. So the vertical commands are on the outside of the function. The horizontal commands are inside of the parentheses for the x value. And now we also have this same kind of split here. So if my k value is bigger than 1, so if my k values, if my numbers inside here are bigger than 1, then we're going to have a horizontal. We're going to have a horizontal compression. So we're actually going to not stretch it. You would think, right? So this is like the opposite way of what we've thought also about horizontal transformations. You would think that if you multiply a number by a big number like 3, like 5, like 10, you would stretch it out horizontally, but actually you don't. You shrink it. So it's a horizontal shrink, actually. It's a horizontal shrink by a factor. And here it's 1 over k. It's not going to be by k. You're going to shrink it by a factor of 1 over k. And this knowing this will be very useful when we talk about trigonometric functions, because you'll be having to deal with transformations of sinusoidal functions such as sine and cosine. So then if k is between 1 and 0, then there's going to be a horizontal stretch. It's a horizontal stretch. Let me make this stretch. By a factor of 1 over k as well. So this is always like the more difficult one to deal with, the horizontal stretch or compression. Does everybody follow me with this, especially with these two here? Is there any questions about this? Yes, we're all good. Oh, sorry, I didn't see that question, Prob. Shift to the left horizontally. Yeah, so that's for the previous one. Here we have stretching now. Now we're dealing with the stretching part. Let's see if I can move this. All right. And then we have like two more. Yeah, we have two more, and I think we're done with the commands for transformations. So there's only two more left. And they deal with reflection commands. So for example, if I have a function, right? And the moment I put a negative in front, does anybody know what's the effect? What's the effect of putting a negative number, a negative symbol in front of the parent function? What do I do to the parent function? Up and down. What do you mean by up and down, Emily? So remember, we shifted up or down if we add a number. So if look at the commands 1 and 2. We shift it up or down when we add by a number or subtract by a number. But this is much different. This is a negative symbol in front. So it's not going to be a shift. So slowly, we're learning ways to manipulate a graph. We're slowly dealing with that. So yes. So when we subtract by a number like this, not subtract by a number. When we put a negative sign in front of a function, we're flipping, or in other words, we're reflecting. So the effect is a reflection. So we reflect graph of y equals f of x. We reflect it across what axis? Does anybody know? We reflect across the x-axis. Across the x-axis. Now, Sydney, how do you know that? It's on the homework. Okay, good. I mean, I guess you can also learn from doing the homework. That's right. An educated guess. That's a very good guess. But let me tell you, Sydney, and for everyone else, you can figure that out without having to guess. Because, yeah, you can either say, hey, it's either the x or the y-axis. I have a 50-50 chance to guess the correct answer. But try to think about what is it actually that I am doing. So I want you all to, yeah, you can also research it on your own, but I want you all to become more perceptive as to what's happening. Like putting a negative sign may not seem like a big deal, but if you understand what's happening, then all these things make a bit more sense. So let's say I didn't have it, right? Let's say I didn't have it. I'll just have a regular function, whatever it is, right? Now, the moment I put that negative sign there, what am I doing? I'm really doing this. I'm saying, hey, for every x value that I originally had, right, with the corresponding y value, negate all of the y values. So all the y values, take all the y values from your original function and negate them. That's what you're doing. You're negating them. So you're flipping the sign of the y values. Graphically, what does that mean? If you go from like, if you choose a point up here and you flip the y value, just the y value, you just flip it, you're over here. You're reflected across the x-axis. So that's why it makes sense when we put this negative symbol on the outside of the function, you're negating every y value, which in turn is the result graphically of flipping it or reflecting it across the x-axis. And then you may say, oh, okay, so that if that happens when I do that, then what would happen when I do this instead? When I put the negative symbol within. So what am I doing here? I am negating all of the, not the y values, but I'm negating all of the x values. So then I should write that down. So this here negates all y values. And this here negates all x values. So if I switch all the x values from my original, so always think about the original function, f of x, then I'm not going to be flipping it across the x-axis. I'm going to be flipping it across the y-axis. So I'm reflecting. So reflect graph of y equals f of x across the y-axis. So here we have all of the commands. We have the vertical shift commands. We have the horizontal shift commands. We have the vertical stretch commands or vertical shrink command. We have the horizontal stretch and the horizontal shrink command. And we have the reflect command across the x-axis, and then we have the reflect command across the y-axis. So far we have the algebraic commands with their graphical effect. Now let's try to see this a bit more with examples. So, and what's going to happen is we're going to have a combination of these commands together. So far we have like these are like my ingredients, right? These are like my separate ingredients. And then you'll see with time, we're going to combine all of these together to create one full variation of a parent function. Okay, so what we're going to do first is describe the transformation. So you should be able to, if you have a function, be able to describe, oh, what's the transformations being applied? So describe the transformation or transformations applied to a function. So we're still going to be talking about in generality, but then hopefully we'll see the specific examples here. So what happens if I give you something like y equals 1/3 f of x? What's the transformation? So what's the transformation that I'm applying? It's a vertical shrink. That's right. So I am vertically shrinking by what? Vertically shrink by what? by how do we say that? We vertically shrink graph of y equals f of x by what? By a factor of 1/3. So we have to say that. So it's a vertical shrink of the graph, pardon me for my, of the graph of y equals f of x by a factor of 1/3. So that's the appropriate wording behind this, okay? So yes, Chen, of course, we know we have to know what's the difference between a vertical and a horizontal shift. We have to, and I stated it before. If and it's right here. Look at 5 and look at 6. What's the difference besides the colors? One of them is k, but it's on the outside. One of them is k, but it's in the inside. So if you have a number outside of the function, vertical. If you have a number in front, inside of next to the x, horizontal. That's how we know. So for example, look at this. Let's do this. So then what if I have this? Y equals f of, and instead of 1/3 outside, I have the inside. What's my transformation here? See, this is good. It's like a versus, reversing them with one another. So what would be the transformation if I have the 1/3 inside? Or horizontal. So see, people say stretch now and compression. So you have to compare what number is 1/3? Is 1/3 bigger than 1? Nah. Is 1/3 between 0 and 1? Yep. So it's a stretch. You have to be careful. It will be a stretch. So this is a horizontal stretch. Remember, this is opposite of what you may think it is. It's a horizontal stretch. So horizontally stretch the graph of y equals f of x by a factor of what? What would we stretch it by? A factor of 1/3? Are you sure, Sydney? You're stretching it. Yeah, it's 1/3, which would be 3. You see that? It's a little like strange to say that, but it's 1 divided by 1/3. So remember when we talk about if we look back at our command, right? We're stretching it by a factor of 1/k, but what is k in this case? K is 1/3. So it's 1 divided by 1/3, which becomes by a factor of 3. So we're stretching it by a factor of 3. I know it's a little weird. It is. It's a little weird, especially the horizontal stretching compression. That's the hardest one. That's the hardest command to master completely. But you start to get the drift of it as you go on. Okay, good. So far we're able to distinguish between, hopefully, between a horizontal and vertical stretch or a compression command. Oh, how about if I give you something like this? Y equals 4 f of x plus 1 plus 3. Do you see this now? Now I have a combination of things happening. So I have more than one transformation here. So what are the commands, or what are the transformations that I have? Yeah. So there's a lot of shifts going on, right? There's a horizontal shift, there's a vertical shift. So there's a horizontal shift, there's a vertical shift, and there's a vertical stretch. So and the order of this doesn't really matter. Whether we stretch it at first or at the end, or we're shifting it first, it doesn't matter for this stuff. So for number 1, what I'm going to do for number 1, is the horizontal shift. So we have a horizontal shift by 1 unit. Then number 2, we have a vertical stretch by a factor of 4. And then number 3, we have a vertical shift by 3 units. So here, this is step 1. Then we can call this step 2. And this is step 3. You see that? So I'm able to break it down by the commands. And with those commands, I'm able to determine what's going to be the effect or the transformation. And then I can delineate exactly what's what. So it doesn't have to be in order. Like I said, Chen, for these commands, it does not matter which one goes first. The result will always be the same. So if I shift it first by 3 units, and then I happen to shift it by 1 unit, oh wait, I should have said, so horizontal shift by 1 unit to the left, and vertical shift up 3 by 3 units upward. So these commands will not produce a different result at the end if I were to interchange or swap or rearrange the order of those commands. It wouldn't. And you can try it for yourself. You can take a function and then shift it by 1 unit and then shift it up by 3 units and then stretch it by 4. Or stretch it first by 4 and then shift it by 1 unit and then shift it by 3 units. You would still result in the same function. So it's not going to affect the order. The order won't affect the result at the end. At least not for these commands. Vertical shift, horizontal shift, and stretching does not affect. The problem does exist when you have reflections. When you have horizontal reflections, then the order will matter. It will. But we don't have that in this particular problem. So I guess one problem that will take care of that will be something like this. So this is where we have to be careful, okay? We have to be careful with this one. So when we have something like this, y equals 1 minus f of negative x. So be careful with this. This is something we have to be careful with. So what's going to be, so now the question becomes, what's going to be the first command? So the order does matter. So let me just write this. Order here does matter. Order of transformations does matter. Here. Due to reflections. It's because of the reflections. Like we have to be careful with reflections because reflections, you can't interchange them with vertical shifts and result in the same result. So does anybody have an idea? What do we do first? Do we vertically shift first? So Prob says reflect across the y-axis. Yeah, so with the reflections, we can actually interchange them within the reflections themselves. So for example, transformations. So he said, Prob says reflect across y-axis. Okay. and then do what? So you're saying this is number one, right? When you have this here. And then when we reflect across the y-axis, what do we do after that? Oh, pardon me. No. That's not what you're saying. You're saying this one here. So when we reflect across the y-axis, we're negating the x values. Remember that? So we're doing this here. Negate the x values, we reflect across the y-axis. Okay. So once we reflect across the y-axis, then what? Right. Then we reflect across the x-axis. So reflect across x-axis. And that's number 2 here. And then finally, the last thing is what? What's the last thing? There's that 1 there, right? What does that 1 do? Are we adding it? Are we subtracting it? And then what does that result in? What kind of transformation? So what does that 1 do when we add it to the function on the outside? It's going to produce what kind of effect? Yep, it's a vertical shift. So it's a vertical shift upward by 1 unit. So the key thing to note is that reflections are done before any shifts, whether that be vertical or horizontal shifts. And the reason why is because first of all, it would go against the PEMDAS, the order of operations. We always apply, for example, parentheses, exponents first, right? So usually these parentheses are done first. And then we do everything outward. And then the vertical shifts, of course, are adding or subtracting on the outside. So those are like the last things we do. And you can think of it as, what happens if I vertically shift first? What if I vertically shift first and then reflect? If I do that, the result will be different from if I were to reflect first and then shift. They would produce different graphs. Whereas in the previous case, it didn't matter what the order was. It would still produce the same graph at the end. You're not sure how it's, oh, probably not sure. Okay. So the reason why it's written this way is to kind of confuse you, right? You're kind of like, wait, what is that? So watch this. Can't I rewrite this? Can't I rewrite this as negative f of negative x? And that 1 here, can I rewrite that? If I were to interchange the order of these expressions here, if I were to change them and just move them around, I would get this. Isn't this the same? Aren't these two expressions the same? Right, so they're the same. So then we're just gonna literally read off. I think this style here is a bit more conducive to our commands. Sometimes we have to change things on our own so that it looks like something we're more familiar with. So we're not familiar with the left side of the equation. We're not familiar with seeing things in this manner, but we are familiar with seeing things like this, except that now we have a whole bunch of commands. We have 3 commands. We have a negative inside the x, we have a negative outside of the function, and we have a +1 outside of the function. Because of these negatives inside and outside of the function, we have our reflections. The reflection across the y-axis is done here. The reflection across the x-axis is done here. And then the vertical shift upward is done by the +1. The +1 comes from this one here. It's just that it's written in a way that we're not comfortable with given the commands that we're used to. But now when we just change that, the +1, we immediately notice, oh, it's a vertical shift up. Like we immediately notice. So yeah, I should have written that out a bit more explicitly. But thank you for that question. Very good. So are we starting to get more comfortable with this? Yeah, so hopefully a bit more comfortable now with seeing the algebraic command and then knowing what it would be in a graphical sense. So we haven't really done the graphical side in terms of seeing the graphs actually transform. But I know you have that, a lot of those in your homework, and we'll do some now. So let's see. Let's see if I want to graph now. I want to graph transformations. So let's see. Let's just sketch. Okay, this is a sketch. So sketch of graph. Sketch graph of g of x. And it's going to be x plus 1 squared plus, oh, pardon me, minus 1 plus 3. So we have this function g of x equals x minus 1 parentheses squared plus 3. The first thing I'm going to ask you to do, or the first thing that you should be able to do, is identify parent function. That's the first thing. So what is the parent function? What is the f of x that we're dealing with? What is it? And then you can go back to your list of parent functions and which one of these is closest to the parent functions that we have. So we have a list, don't we? We have a list of all of the parent functions. So is it a linear function? Is it a linear function? No, because there's no square in the linear function. Is it a power function? Is that the parent function? Is it a root function? No, it can't be a root. Is it reciprocal? No, it's not 1 over anything. Is it absolute value? No, it's not absolute value. So the only one that seems to work, right, is the power function. But what particular power function is it? So this is a power function. The power function will be a power function. Does anybody know what's the specific end value? What's the specific exponent that's associated with this? What's the only exponent that we have here for g of x? The only exponent is what? It's right there. 2. Right? So the parent function would be what? It would be quadratic. Yes. The parent function is x squared. That's it. That's it. X squared is the simplest quadratic function we have. Hence, parent function. You could think of it as every other, I don't care what quadratic function you have, every other quadratic function comes from the parent. That's why we call it the parent, because from the parent, everything comes from it, right? Like the offspring. So every other quadratic function is a transformation of this simple x squared. And we know what it looks like, right? We already know what this looks like. We should know. So again, this is just going to be a sketch because it's not perfect. So boom, here we got it. Here we have our parent function, y equals x squared. We know this. We know this. But now, what are we doing to this function x squared? What are the transformations? You see this? You starting to piece things together? I hope so. So what are the transformations now? Now that we know how to read transformations, what are the transformations? And there's only two of them. So what are we doing to x squared to get to g of x? What commands do you notice immediately? So it's a vertical shift of 3. That's right. And what other shift is there? A horizontal shift of 1. Right. And if we shift it by 1, where are we moving? Left or right? So let's start with the horizontal shift first, because we always want to start with the x values first. So horizontal shift by 1 unit to the what? To the, is it left or right? To the right. To the right, to the right, right? You guys know that song, or is that, am I too old for that? Okay, horizontal shift by 1 unit to the right. And then we have a vertical shift to the vertical shift upward by 3 units. So what does that mean? What does that mean? That means I'm saying this, hey, look, I'm going to take this guy. I'm going to take this graph. I'm going to shift it over by 1 unit to the right, and I'm going to move it up by 3 units. So then what's going to happen? Let me copy this. So then I'm going to shift it over by 1 unit. And I'm going to change the color. Let me change it to this green. So this green represents the first shift. This is step 1. Let me change this to the color here. So this is step 1. This is 1 unit. And then what's going to happen next time? I'm going to take this guy here and then move it up, right? I'm 1, 2, 3, somewhere up here. And I'm going to change the color as well and make that the blue. Is everyone following this? There's a whole bunch of colors here. But I just want you to see the sequence. I want you to see the sequence of transformations and how we are applying it. Do you see what we just did? We moved it first to the right. We move this to the right. And then we move this up. So we did this by 3, plus 3. And then we did this by 1. 1 unit to the right. And 3 units up. And this here, it represents the graph of g of x. That's what it is. That's why it's important to understand parent functions. It's important to understand transformations upon the parent function so I can figure out what is the result. And then when we talk about, for example, vertex, right? We like talking about vertices. So the original vertex is 0, 0. Now, what's going to be the vertex for g of x? What's the minimum point? Well, if I moved it to the 1 unit over, then my vertex here would be what? My vertex here would be 1, 0. And then I move it upward by 3 units, so I only affect the y values. So then the vertex here would be 1, 3. And for those of you who remember, this is just like a little side note. For those of you who remember the vertex form, remember the vertex form of quadratics? It's a parentheses x minus h squared plus k. Do you see how this expression here represents a transformation of what? Of x squared? And that's why they say, hey, what's the vertex? We're going to talk about this next time. The vertex is what? H comma K. Do you guys remember this? Do you see how it's better understood? The vertex form, what I'm trying to get at is, it's not just a formula. It's just like someone just made it up. No, no. There's a reason why. There's a rhyme and reason as to why the formula is what it is. Now that you have this perspective on transformations, you have to see, oh, this H and K represent transformations, commands. This is a vertical shift, either right or left by H units, and this is a vertical shift, either right or up or down. This is a horizontal shift, either left or right by H units, and this is a vertical shift by K units up or down. And that's going to affect the vertex. That affects the vertex. So that's how we're able to build upon previous knowledge. Good. I hope so. Okay. Okay, good. So we did that. Graph transformations. Okay, good. Now let's find equations of transformations. So I should say 4 transformations. So an example, let's say I start out with my function being the square root of x. And let's say now I tell you, now I'm going to tell you what the transformations will be. I'm going to tell you, hey, you know what I want? This is what I want. I'm going to give you my order. My order is, hey, I want some square root of x where you reflect it. You reflect across the y. And then after that, I want you to shift it upward. Shift upward by 1 unit. And then you'd be like, yes, sir, I'll be right there. So then what would be g of x then? Can anybody tell me what the function will look like after I transform, after I apply these transformations? What would be the algebraic result? So if I want to reflect square root of x, right? I want to reflect it across the y-axis. What's the algebraic command for number 1? What is it? Place a negative in front of the x. Right. I want to reflect across the y-axis. So the negative will not be in front of the x. So be careful. If you put it in front of the x, you reflect it across the. Oh no, you're right. Yes, you put the x, the negative in front of the x value. Sorry, I'm thinking about that the y value, the x-axis. So yeah, that's right. So I'm going to put a square root. I'll put a negative in front of the x. So that's step 1. That's 1. And then I want to shift it upward. Plus 1, right? So we had the plus 1 at the end. So this is the result. So Prab, you're having a problem with the 1 unit upward? Yeah, if it's 1 unit upward, all you have to worry about is adding 1 to the function f of x. Remember when we add by 1 like this? Or plus k, you see that? This is my function, and I'm just adding by 1. So then I'm adding by 1, I'm shifting it upward. The reflection across the y-axis, I negate the x value inside. If I had to reflect it across the x-axis, then I would put the negative outside. You see that? It does make a difference. It does make a difference. And then what would be the graph? What would be the graph? The graph of, let's graph both of them, of f and g. So first of all, you need to know the graph of the parent function. What's the graph of the parent function? The square root of x. We know that square root of x, what it looks like. We know it looks like a half of a parabola opening to the right. So this is y equals the square root of x. And then what's going to happen? Well, I'm going to reflect it across the y-axis. So I'm going to have the same exact thing, but now I'm going to have it this way. This here would be y equals the square root of negative x, correct? But that's not the end. That's not the end, because I want what? After I want the reflection across the y-axis, and I should say that. This is the y-axis. This is the x-axis. So after I reflect it across the y-axis, I move it up by 1. So then I'm going to move this up by 1 here. This will be just the same thing, just moved up by 1. So this is going to be y equals the square root of negative x plus 1. That's it. So this would be f of x. This is where we start with. And then this is g of x. G of x. Is everybody with me with this? I'm glad. I'm glad. So the most important part of all of this, well, not the most important part. There's actually two important things. Two important things to understand transformations well is the following. You need to know the parent functions. So what are power functions, reciprocal functions, root functions, absolute value functions. So if you have that basic knowledge of what they look like, how they look like algebraically, how they look like graphically, then once you have that, then you combine that with knowledge of what are the transformations and the commands for the transformations. If you have those two things together, then understanding transformations is a lot easier, better, and it will go well with you. It'll be okay. Everything will be okay. Okay, so those are transformations in a nutshell. We're gonna revisit this every time almost. Like when we learn about different functions, we're gonna be studying the parent function, and then we're gonna be studying the transformations upon the parent function. So for now, we only have the parent functions that we've discussed. Eventually, we're gonna add more. We're gonna add, like I've said before, we're gonna add polynomial functions, and then we're gonna add, which are related to power functions, and then we're gonna add rational functions, and then logarithmic, exponential, and then finally trigonometric. All right, so talked a lot about transformations of functions. Good. Now we're gonna talk about the things the different operations we can do with functions. So far we've done transformations on one function. Like we're applying things just to one function. Now our question is, can we have two different functions? And what can we do with two different functions? Can we add them? Can we subtract them? Can we multiply them? Can we divide them? And the answer to all those questions is yes. If you have two different functions, we can add them. If you have two different functions, we can subtract them. If you have two different functions, we can multiply them. If you have two different functions, we can divide them. So we're gonna study the operations on functions. So we can add, we can subtract, we can multiply, and we can divide functions. No problem. That's no problem there. It's just that we have to understand certain notation for this. So the function notation, okay? So we have function notation. We're gonna make another table here. So we have function notation. We have yeah, the kind of operation, right? Type of operation. And this is the just another version of it, another algebraic the algebraic form, the algebraic form. So there's only 4 of them that we're going to discuss really quickly, and then there's another one which is only applies to functions. And that's the 5th one. That's the 5th operation. So type of operation that exists, we can add them. So there's a sum, and what's the notation for that? The notation would be if I have 2 functions, f plus g parentheses x. That's the notation for the sum. And what does that mean? That means I am adding f of x to g of x. That's what it means. Okay, and that's all it is. It's kind of intuitive. And if there's a difference between 2 functions, then obviously we would use a subtraction symbol. And this would mean f of x minus g of x. Okay? So we're just learning the function notation for now. Next thing is what? The product. The product is going to be what? Fg. When you have Fg like this, just together, or if you have like a dot in between f of x, then this is going to be f of x multiplied by g of x. And then the last one of these common ones is going to be division or a quotient. Yeah, division. Right? So division. And I should say yeah. And so then the division looks like this. F divided by g of x. What this means is that f of x is being divided by g of x. That's what it means. Okay, so it doesn't seem too crazy, right? It doesn't seem like much of a problem. So let me just give you a few examples here. And one thing to also include here is what we're going to care about is the domain. Okay, so the domain, because we care about the domain of functions a lot. And the domain of the sum, the result, is just going to be the intersection of f. So the domain of f, we intersect that with the domain of g, and so on and so forth. This is not extreme. This isn't more on a technical scale. It's important on a technical scale. And it goes on for all of them. But the division symbol, that one is a little bit more special because we want the domain of f and the domain of g. But we have to be mindful that g of x cannot be 0. We can't have the denominator equal to 0. So we have to be mindful of those x values as well in our domain. And we'll see that with examples. I hope we can clarify that with some examples. So suppose I have 2 functions, right? So I have f of x, for example, I was Let's make it simple, not nothing crazy. So it's supposed to have a function, 5 minus x, and I got a function g of x squared minus 3x, okay? And then I want to find all the different ways we can combine them using these operations. So for example, if I want to find the sum, what's going to be the sum? The sum is going to be the function where I have f plus g, right, of x. What is that? That's f of x plus g of x, which is what? 5 minus x plus x squared minus 3x. Combine like terms, and what's going to be the sum? It's going to be x squared minus 4x plus 5. Okay, that's my sum. That was it. I just added them together. That's all I did. And then what would be the domain? What would be the domain of the sum? Well, let's look at what we have originally. This is what? What kind of function is this? This is a linear function. And what kind of function is g of x? This is a quadratic. One thing about these two functions that are nice is that both of them, the domain for both of the functions are all real numbers. So the domain of f and the domain of g are all real numbers. What's the intersection of all real numbers with all real numbers? It's all real numbers. So the domain here is negative infinity to infinity. Pretty straightforward, I hope. The second thing is, what's the difference? So it's going to be y is equal to f minus g of x, which is saying f of x minus g of x. What's f of x? 5 minus x. What's g of x? X squared minus 3x. So this is 5 minus x squared plus 3x. So the result will be negative x squared plus 2x plus 5. That's my difference. It's another quadratic, but you see it's a bit different from the sum. They all have a plus 5, but then my x squared here, opposite signs, and I have negative 4. This is a positive 2. What's my domain? Well, again, I compare the f and the g, right? We talked about it. There's linear, quadratic. Both of those functions have all real numbers for the domain. So the domain here would also be all real numbers. Done. Next, what's going to be the product of these two functions? What's going to be f of x multiplied by g of x? What's f of x? 5 minus x? What's g of x? X squared minus 3x? Multiply. How do we multiply? FOIL. We get 5x squared, pardon me, minus 15x minus x cubed plus 3x squared. Write it from using the highest term first, the highest power first, negative x cubed, and then you have plus 8x squared minus 15x. That's going to be f g of x. Done. And the domain of the functions are both intersection, right? The domain is still going to be the intersection of the negative infinity to infinity, which is negative infinity to infinity. So far, so good, guys. Does everybody see what I'm doing? I'm just adding the functions when I sum them. I'm just subtracting the functions when I subtract them. I'm just multiplying the functions when I multiply them. That's pretty much it as to what we're doing as so far. But now we have to pay a little bit more attention to when we divide. So what happens when I divide them? F divided by g of x. Well, I'm taking f of x as my numerator, g of x as my denominator. What's f of x? 5 minus x. What's g of x? X squared minus 3x. And that's it. I can't do much after that, right? But then what's my domain? My domain would be all real numbers because the numerator are all real numbers, the denominator are all real numbers. But the issue is, what's the issue? The denominator cannot equal 0. So there are x values that make my denominator equal to 0. So what do? We find them. We find those x values that make my denominator equal to 0, and then we exclude them from the domain. So then we say, hey, x squared minus 3x could equal 0. Factor out the x, and you get this. You get x equals 3 and x equals 0. Those are two bad points. Those are the bad points. So then what do we say? If we put this on the number line, right? At 0 and at 3, I exclude them, but I shade everything else. We've done this already. And so then this would be what? Negative infinity to 0, union 0 to 3, union 3 to infinity. Any questions about this idea of adding, subtracting, multiplying, and dividing functions? I don't think anything is new from this. The only new thing is the notation. I'm pretty sure this may be new. Like when you write the functions in this way, you should now be able to determine what kind of operation is being applied to the functions, whether it be division, multiplication, a difference, subtracting, or addition. So are we good with this? So let's stick around with the same example. So can you evaluate these functions now? Evaluate the following. So what if I want f plus g of 2, and then I want f minus g of -1, and then I want fg of 0, and then I want fg of 1. So we can evaluate function as well. F plus g parentheses 2, what does that equal? Well, that equals f of 2 plus g of 2, doesn't it? So what's f of 2? Well, what is f? F is 5 minus x. So this would be what? 5 minus 2 plus, and then what's g of x? G of x again is x squared minus 3x. So this would be x squared, 2 squared minus 3 times 2. Do you see what I'm doing here? I'm evaluating each of these functions individually and then combining them. So this would be what? This would equal 3. This would equal what? 4 minus 6. So 3 plus 4 is 7. 7 minus 6, that's equal to 1. So the result, when I evaluated f plus g of 2, is 1. Now, the same thing happens here. F minus g of -1, it's f of -1 minus g of -1. So find f of -1 individually. This will be what? 5 minus parentheses -1 minus parentheses -1 squared minus 3 times -1. There's a whole bunch of stuff here happening. But again, we're taking things individually and just finding them, the result individually. 5 minus -1 is 5 plus 1, which is 6. -1 squared is +1, minus 3 times -1, it's plus 3. 1 plus 3 is 4, so it's 6 minus 4. This equals 2. So we're building upon this idea of functions. Like I told you, we're only talking about functions this whole way. This whole semester. Functions. Now what about this? F of 0 times g of 0. What is this? Well, first of all, what's f of 0? It's 5 minus 0. Multiply that by 0 squared minus 3 times 0. Uh-oh, what happens? 5 minus 0 is 5. 0 squared minus 3 times 0 is 0. 5 times 0 is 0 in this case. That would be a different number, but anyways. I multiply those two numbers out. And then lastly, f of g of 1 is the same thing as saying f of 1 divided by g of 1. What's f of 1? Well, what's f? It's 5 minus 1. What's g? 1 squared minus 3 times 1. 5 minus 1 is 4. 1 squared minus 3 is 1 minus 3, which equals 4 over negative 2, which equals negative 2. Done. So we can add, subtract, multiply, divide functions. We can find the domain of those functions. We can also evaluate those functions now that we know what these symbols, what this expression, what this notation even means. Okay, so we're getting more and more comfortable with functions, I hope. Now the next thing after we learn why do you use 5? Because my function originally, my function that we're using the whole time is 5 minus x for f. So that's why every single time I use f, there's a 5 that appears. You see that? Yeah. So every single time I'm applying f of anything, you see the 5 minus. F of 1 is 5 minus 1 because that's how the function f is defined. And similarly, g, you always square and subtract by 3 times the input. It's because of the way that the function was originally expressed. Okay. So now you're like, okay, nothing special, right? It's like, okay, we get it. We add, subtract, multiply, divide. We've been doing this for numbers for the longest. We know how to deal with this. Oh, we're just adding this to functions now? All right, great. But now, what makes functions a bit different, there's one more operation here that I did not discuss. And we're going to discuss this next time. The next operation that we're going to be considering is composition of functions. So that's when you're like, wait, that's an actual thing. So what we're going to be discussing next time are what's called composition of functions. Now, this is what makes functions a little special to talk about, because you can't talk about composition of numbers. So we haven't seen this kind of operation yet, because with numbers themselves, we don't really do this operation. It's not a viable operation. But for functions, there's such a thing. And just plainly in words, for those of you who haven't heard of what a composition of functions are, is basically when you apply one function and you plug it into another function. That creates a composition. So that's the cool thing about functions. You can apply one and then apply the other. And you can do this multiple times, actually. You can apply a function to itself. So a really simple example of this, and let's say I have a function like 5 plus, no, let's use x plus 2. Now, my function goes from x, then it goes into a function, right, called f, and the result is what? X plus 2. But then, can't I just apply this again to the same function, for example? Just as an example. What does the function do? It takes whatever it is as the input and then adds by 2. So I'm going to have x plus 2, parentheses plus 2. So the result will be x plus 4. So if I'm applying the function to itself, the result is x plus 4. And we'll see more of this next time. We'll talk about the notation and finding a domain for composition of functions. So that's when things get a bit more interesting.